Good morning, everyone. I'm Simone Perriello, and today I'm going to talk about the intersection between two research areas, which are cryptography and quantum computing. And that is my topic of research. Okay, imagine it's 10 years from now, and the newspapers runs this title, the cryptography is dead, the apocalypse is near. Why is that? Maybe because someone around the world announced the discovery of a quantum computer, or the construction of a quantum computer with a huge number of qubits. So panic spreads across the users, the citizens, the governments, banks try to counteract and try to analyze what is the threat posed by quantum computers. So why this is a threat? Well, back in 1994, this guy on the top left of the slide, Peter Shor, shocked the world with the revolutionizing quantum algorithms capable of breaking modern public key cryptography in a linear amount of time, which is exponentially faster than any known classical algorithm. Recent estimates say that RSA and elliptic curve cryptography can be broken using around millions of qubits, which is very far from what we are. Indeed, you can see on the top row of this slide that IBM, a few weeks ago, announced the construction of a chip, of a quantum chips, with just 433 qubits. However, it says that it can have a chips in its plans by 2030 with 1 million qubits. So, of course, governments and banks and every actor has to counteract this threat right now. And indeed, for example, governments such as the US government, through this agency, the NIST agency, is launching these standards, this call for standards that tries to replace the modern public key cryptography with new cryptographic primitives capable of resisting quantum attacks. Okay, for example, NIST is in its 4th round, and it's planned to propose draft of standards by next year, and wide deployment by 2030, of course. But also China and Germany and many other governments are doing the same. And that's where scientists kick in. On one side, there are researchers proposing new crypto schemes capable of resisting quantum attacks, hopefully. And on the other side, there are bad guys like me that tries to break these toys and see how much do they resist to quantum attacks. And we, in my team and I, specifically implemented concrete quantum circuits to attack a family of crypto schemes, which are the code-based crypto schemes that are one of the major candidates to post-quantum cryptography. And I stress the concrete part because we need this concrete analysis in order to fine-tune these cryptographic primitives proposed, for example, by NIST. And in doing my research, I used two quantum frameworks, two principal quantum frameworks that are Grover framework and Quantum Works. I want to just stress a few things about these slides, which are the improvement on the state of the art, which can be read as 2 to the power of 18 on the first row to the power of 20. So in general, with respect to the state of the art, which was theoretical before our work, we improved in a factor of, on average, 2 to the power of 20 for all the families of crypto schemes proposed on the left and all the security level requirements. And on the last column, you can see we discovered that one family of crypto scheme, the McElizy at level 3, failed to reach the security target demanded by NIST. So in its current form, it's not safe. Finally, and I conclude, in doing my research, in doing my circuits, I implemented different kinds of circuits that can be of independent interest, such as circuits for Gauss-Jordan elimination, quantum circuits to order bits, to permute columns or rows of a matrix, compute the Hamming weight of a string, to generate a superposition of bit strings with a given weight. And I want to stress also that this algorithm can be used in different parts, such as for different problems, such as computing the spark of a matrix and solve the 3D matching problem, which is a well-known combinatorial problem. Thank you for your attention. If you want to mail me, this is my email address.